I'm a teacher Qn.consider Masame. Welcome to Qn Physics. We have a question from SERWAY&JEWETT, chapter 35, question 41. Consider a common mirage formed by superheated air immediately above a roadway, and a truck driver whose eyes are 2.00 meter above the road, where refractive index are 1.000293, looks forwards. She perceives the illusions of patch of water ahead on the road. The road appears wet only beyond a point on the road at which her lines of sight makes an angle of 1.2 degrees below the horizontal. Finds the index of refraction of air immediately above the road surface. Let us consider how mirage is formed first. I have the sun's clouds here, and this is observer eye's position. Now the rays from point P is undergoing a series of refractions, as we know that the air on the ground is superheated and become less denser, while the air above it is a little bit warms to a cold air which is denser than this warm and this hot air, and therefore when the light is moved from this cold or denser air is undergoing refractions, where refracted rays is always towards the normal. As you can see, the refraction series reaches the point O. Then from this concept, we just explain it by assuming there is continuous change of refractive index here due to the continuous change of optical density of these air molecules. As when it is near the surface, the density is lower, and as it is keep increasing as going to the upper surface to point P. Okay, as these rays move down, it reaches a point where the condition for critical angle is fulfilled. As this condition for critical angle fulfilled, now the refracted rays angle is equal to 90 degrees, and now the incidence angle becomes a critical angle. Under these conditions is where there is a partial weak rays that is reflected to point N, and this process we call it a total internal reflections. Now we will consider this total internal reflections when this critical angle, this incidence angle become greater to critical angle. Under these conditions is when the total internal reflection take place. And now the incidence rays now PO is diverted to from its normal directions, and now it's start moving up. As it's moving up, remember the increasing optical density is up to point N. Then this refracted rays is always away from the normal, as from less density to denser media. Now the extrapolated backwards refracted rays away from normal is giving us an image to every distance L, which is approximately equal to 100 meter. Therefore, at each point when the observer is moving and the position is about 100 meter, the observer will be able to see the visual image of the clouds or any object which is standing tall at the ground. And this visual image is appearing to him or to her as a patch of water. Therefore, this image is formed due to total internal reflection, and it is due to extended backwards reflected rays, that is ON, to a point as you can see on the ground. Therefore, the radius of the circle of total internal reflections, which is under this cone N or P, is equal to NM, and which is equal to a half L, and the height from the eyes to the ground is always a half, because the distance from the law of reflections, the distance of the image is the same as the distance of object, which is clouds is the object from point P to the boundaries, and from this boundaries to this one is the same distance. Okay, remember this when we assume now from this questions, we assume that now we have non-uniform media. It's just only we have a two media which is non-uniform. For rare media, this which is constant media, which is rare, which is hot, and for dense media, which is a constant layer, which is cold. This is non-uniform layer, and this is another second non-uniform layers, which is hot for rare air and for dense air. From this concept, we know that a point O is where total internal reflection will take place, and from this concept, the rays will be straight at an angle 1.0 degrees from the line of sight NP. I get reflected to point to the observer eyes, and the image will be formed here as usual. Okay, for this case, we will be able now to calculate the refractive index for hot, that is rare air, with respect to this refractive index for cold, which is dense air. Now consider the Snell laws of refractions. Now for cold times sign for incidence, for hot sign of refractions. Remember, this is hot refraction. Now for sign of refraction, we know that R is refracted angle is equal to 90 degrees. Now is equal to 1. Now where the sign of incidence becomes equal to critical angle. Now from mixing the subject here, we have refractive index for cold times sign for critical angle. Now we know that this angle 1.2 degrees is this one, and this one is 90 degrees for this triangle, and now the incidence angle here is, which is equal to critical angle, is equal to 88.80 degrees. As we take this 1.2 degrees, we minus from 90 degrees, and we remain with this angle, which is 88.80 degrees. Now from here, we remain with this, we finally arrive to this answer, which is 1.00007 approximately a refractive index for this hot air. Thanks for watching. Please like, share, comments. Don't forget to subscribe to this channel for more videos like this one. Thank you.